So welcome to Cloud Native Data Pipelines. I'm Sid Anand. A little bit about me. Over the last 16 or so years, I've worked on end-to-end data infrastructure. Most of my time has been spent at companies that are typically consumer-facing, high-scale traffic, high-traffic companies like LinkedIn, Netflix, eBay, and Etsy. About 2.5 years ago, I joined an enterprise SaaS company that works in the security space called Agari. And they're doing some interesting work with data in the cloud. And I'll talk to you about that today. In my spare time, I'm a co-chair for KubeCon San Francisco and London. I'm a committer on the Apache Airflow project. And I'm a father of two, a rambunctious 4.5-year-old boy and a 7-month-old girl. So Agari, what do we do? So we make email safe again, for those of you not familiar with it. Now the thing is, email has actually never been safe. Since the 1970s, with the advent of the SMTP protocol, it's only been more recently that security protocols like SPF, DKIM, and DMARC have been developed, many of which were developed by members of my team. It's not in widespread use at this time. So you still encounter these sorts of scenarios, right? You get an email from your bank or credit card saying there's some sort of suspicious charge, and you need to log in immediately and verify the charges, or maybe your account will be closed. And essentially, you will get phished in most cases because your bank tries not to send you things like that via email, and most people don't realize it. So what do? Our first product, which was launched a few years before I even joined, was to protect consumers in a B2C company. So most of my former companies, LinkedIn, eBay, PayPal, Netflix, used Agari to secure the email channel between them and their customers, so that it reduced the chance of their customers being phished by an email that looked like it was from Netflix. When I joined about 2.5 years ago, we tried to take this technology and apply it to the enterprise, so that enterprises could also be safeguarded in this way from inbound email. So you might have heard many years ago, LinkedIn sort of lost 17 million passwords. Didn't really lose them, they just let other people have them. There was some discussion of an email-borne route for that attack. And that's sort of the case that we're trying to prevent, right? More and more loss of data at the enterprise level. So our first version of our product was a batch product. So enterprise customers deployed one of our sensors in their data center, and every 15 minutes, they would send us a file which contained email headers. And we would analyze that data in the cloud. We would use a subset of it to train models. And for the most part, we would score that data so we could assign a trust score on a range from trusted to untrusted for each email. And we would provide a visibility dashboard to our customers, which would show statistics on their mail flow. About a year ago, we started developing a near real-time product. In the near real-time use case, mail flow is coming in, and our cloud-based service is applying those trust models, or in some cases building some on the fly, and again showing a visibility dashboard, which now is a real-time dashboard. But in addition, we're also basically executing a control flow, where based on some policy, we can send a signal back to our sensor to either quarantine the email, label it, or allow it to pass through. And in most cases, we're running essentially 3 nines between the sensor and back to the sensor with 3 seconds of latency. And majority of that time is actually spent over the public internet that we don't control. So within our cloud deployment, we're actually, in many cases, sub-second. So what's the reason that this is called cloud native data pipelines? So if you've worked at big data companies, like LinkedIn or Facebook or Twitter or Google, their data engineering teams are huge. 500 is not an unknown number, right? And they're running their own custom data pipelines on hardware. And for, if you remember Dean's talk, there was a reference architecture with lots of open source technologies. Typically, in a large company, each of those teams would be supported, each of those boxes would be supported by a different team. Whether you're running Kafka, you need a team on hand to patch it if it needs to be patched, to do some operations on it, to configure it, all of that stuff. Now, if you work at a startup, you don't have hundreds of engineers. You may have one engineer working on the data pipeline. Our company has about 10. The total company size is 20 engineers, 10 of which are working on the data pipeline and data science side. And they're running in the cloud in most cases. So are there things that these small companies can do so that they get the same sort of comparable pipelines that you'd expect at a Facebook or a Twitter? And the answer is yes. If you adopt some cloud native techniques and some open source technologies in a certain way, you should be able to get highly available, highly scalable, low latency data pipelines to do interesting things like predictions. So before we get into an architecture, we should define what are some desirable qualities of a resilient data pipeline. And for us, there are 4 aspects: correctness, timeliness, operability, and cost. So correctness essentially means that we should have data integrity end-to-end in our data pipeline. We shouldn't lose any data. We shouldn't corrupt any data. And since we're building, like the type of pipeline we're working on is a predictive data pipeline, is generating predictions and ranks and scores, the data distribution out of the pipeline should be as expected. We shouldn't all of a sudden find that 99% of the messages we're generating are considered phish or untrusted. In terms of timeliness, whether you're running a daily, hourly, or near real-time pipeline, what's really important is that the SLAs are met. Whatever the SLAs are, they need to be met. Because in our case, we may be holding an email in someone's mailbox until we've analyzed it and said it's safe to deliver. In terms of operability, if you've worked in these large data teams, you'll find that a very common problem is operational fatigue. Majority of the time, or most of a data engineer's time at these companies, is just keeping things up and fixing data problems. I'll talk about quick recoverability, but one major problem that happens in data pipelines is that if there's a bug, once you fix the bug, you have to fix all of the data that flowed downstream and contact all of those teams and basically fix all of the data that you've corrupted all the way downstream. And that results in a lot of operational fatigue because every bug has a large blast radius. Another thing that's important for operability is that we have some sort of fine-grained monitoring and alerting so that we can check that we're meeting our correctness and timeliness like SLAs. And then quick recoverability. So there are 2 aspects of designing a system for reliability. One is called mean time between failure, and one is MTTR, mean time to recovery. So I haven't included a slide here, but there is an interesting thing on a talk I gave last year at this conference. There's this comparison of a Jeep to a Rolls-Royce. A Rolls-Royce is designed to operate really well within its operational boundaries, like nice roads on the Autobahn, right? But if you take it off-roading, it's going to break down. And then you're going to spend a considerable time fixing it. Whereas a Jeep was designed by the people who created it to be taken outside of its design boundaries. They don't really need to know what you're going to do with the Jeep, but they expect that you will break it. And when you break it, it should be really easy to fix. So on YouTube, if you search for a Marine Corps team reassembles Jeep in 4 minutes, you'll see what I mean. So that's sort of what we want in our data pipeline. Bugs will happen. We just need to quickly recover when that happens. And finally, since we're running in the cloud, one of the promises of the cloud was pay as you go. So we can leverage some aspects of auto-scaling and maybe lambdas to reduce our cost of running a data pipeline, something you can't really do in your own data center. So what do predictive analytics look like at Agari? So we have two classes of predictive analytics. One is building and training models, and the other one is applying those models in either a batch or near real-time pipeline to score them. And today's talk is mostly going to focus on applying the models. So let's look at an example of our batch pipeline architecture. So we have, say, 3 companies, enterprise A, B, and C. And they're getting mail coming to them all of the time. And they've deployed a sensor, an Agari sensor, in their data centers. And in our first version of our product, which was batch, every 15 minutes, our sensor would upload a file into S3. At the top of the hour, we'd have we use Airflow for our workflow engine. And I'll talk a little bit more about that later. But we essentially have a workflow engine called Airflow that will run a Spark job to score that data and generate some aggregate statistics once an hour. And it will output that data into a different path in S3. We've set up S3 with what's called SNS notifications. So as data lands in S3 in this output bucket, notifications are sent on simple notification service SNS, which will queue them in simple queue service. So SNS is a push-based topic queue, and essentially what it does is for every event it gets, it'll notify a bunch of subscribers. And SQS is a queue service that will actually retain all of those messages, but it allows single message consumption. And if you want to learn more about this, you can have a look at last year's talk. We're actually going into details of how these two work together. But I'm sort of assuming that, just to get a raise of hands, how many people are familiar with SNS and SQS? OK, that's very good. Now, as messages flow into SQS, we scale out what we call our importer layer. So our importers are Ruby jobs that will read these messages and import them into our Postgres database. So S3 contains all of our data, all the input data, all the intermediate data, all the output data. But our Postgres database is used to feed a subset of that data to our web app, so that it's only the subset of the data that we need to show in our visibility product. And the importer's job is to efficiently insert all of that data into the Postgres database. And we have Airflow basically managing this entire process, also checking the quality and loss characteristics of the data on each step in this pipeline. So let's look at some of the architectural components here, right? The first one is S3. S3 is where we're essentially building our data lake. It's scalable, available, performant. It's serverless. We don't need to manage it. It's used to store all of our data, as I mentioned, our input, intermediate, and output data. And all of our data science processing goes against S3. So essentially, it's like HDFS, but we don't really need to worry about scaling it for data growth. For messaging, we're using a combination of SNS plus SQS together. By using them together, we get the benefits of both. And essentially, we get a reliable transactional pub-sub. So what that essentially means is we get the benefits of pub-sub, such as multiple topic listeners, but we also get transactions. So when you consume a message, you actually have to send an ACK to let SQS know that you've consumed it. Again, it's serverless, and it's infinitely scalable and performant. We have 2 cases of processing. So for our data science processing, which in this case is scoring, aggregations, model building, we use Spark. And we've used it in both flavors, both EMR and also running our own. And it's spun up in both cases by Airflow. Airflow will spin up a cluster, whether it's EMR or our own image running on EC2, do whatever processing is required, and then spin it down. And Spark has a very nice programming model, but it's like very complex to debug. And I think one of the speakers in this track later will sort of go into the details of Spark. And if you haven't used it, you'll get a appreciation of how complex it is, and powerful, of course. And for general processing, sort of like some business logic, we just take whatever type of service we have and we encapsulate it in an auto-scaling group. And we just let Amazon manage that auto-scaling group so it's always up and scaling for traffic. The workflow engine we're using is Airflow. So it coordinates all the Spark jobs and other complex tasks. It's lightweight. It treats DAGs as code, so config as code. If you've used other type of workflow engines like Uzi or Azkaban, you basically have to wrestle with YAML and zip files of YAML and XML files. And the approach that systems like Luigi and Airflow take are just treat this as normal code and use your development processes to manage them. It does have a little bit of a steep learning curve, especially around operations. And that's because Airflow is not very opinionated about how you'll run it. It just sort of gives you a sense of how to run it in one box, and you sort of have to make it scale. And finally, the database we use is Postgres for no better reason than our web app developers picked that. And so we're using it. And since they are Rails people, like Rails people love Postgres and vice versa. So in this model, right, like 3 of our services are not managed by us, and 3 of them are. And that informs you a little bit about how we run. We are such a small team, we can afford to run everything ourselves. And when we have a choice, we will always pick something provided by, say, Amazon. And when we don't find an adequate solution there, we will choose to manage it ourselves. And in this case, there was no real good workflow engine provided by Amazon. And to some extent, like, as I mentioned, sometimes we use EMR and sometimes we don't, because there are downsides of using it. So let's talk about cost and timeliness, right? When we were running every day, right, for 23 hours of the day, we only paid for the EC2 instances that ran Airflow, our database, and our web app. And at the end of the day, we ran a full daily run. At that point, we paid for running AMR for an hour and the importers for an hour, and any messages that we had to pay for on SNS and SQS. So we were very cost efficient. So we built an infrastructure that didn't have just a bunch of standing nodes that we were paying for, even if they were reserved instances. When we went to hourly, things changed. We actually were, whether we ran for a minute, 5 minutes, or an hour, EC2 basically charges us for the full hour. So we were actually not saving any money with this architecture. We were when we were daily, but once we went hourly, we were saving nothing. So one idea was for us to just move to Lambda. Lambda charges you up to 100 milliseconds rather than up to the hour. So we found it in general with some back of the envelope calculations to save us about 100x the cost. So 1/100th of the cost of running the equivalent load, even continuously on EC2, would be running on Lambda. It's like a penny versus $1. So it's quite a good cost savings if you're considering Lambda. What about timeliness, right? So in the batch world, we're running every hour. And sometimes, as new customers come online, our data volume is growing, and our Spark jobs take longer to run, and our importers take longer to import that data. And the challenge we have is completing all of it within an hour all the time. So Airflow, since it manages the spin-up of Spark, we can just configure through an Airflow variable the number of workers and the instance type, which defines the memory and CPU characteristics of that Spark cluster, right before the next hourly run. And the next hourly run will automatically spin up a bigger, stronger, larger cluster for Spark. What about the importers, right? How do we scale the importers out? So we adopted this thing called auto-scaling. How many of you, just to see a show of hands, use auto-scaling? Okay, it's about 10 people. Right, so what auto-scaling gives us, and I'll tell you why this is important. So we have an hour budget to finish our workload. And sometimes Spark will take 50 minutes. And what that essentially means is we have 10 minutes or less to import all of this data into our database. And we need some way to make a cost performance trade-off. And an autoscaling group lets us define a max and min of the group. And if we're finding our Spark jobs are just taking longer and longer, we just raise the max. We pay a little extra, and we get the importer will take less time. And I'm going to talk to you a little bit about the autoscaler now. But essentially, what it does is it listens to an SQS queue, and it will scale out based on some characteristics of that queue to get a higher throughput as needed. So our first approach at autoscaling used what's called a CPU metric. So I'm going to sort of talk about that right now. So as I mentioned, we have these importers. And one way to scale a cluster of importers in or out is based on the average CPU of the cluster of importers. And this is a common first step for anyone using autoscaling, is they'll say, OK, I want to scale this EC2 resource. Maybe CPU is a good measure. So let's use the average CPU. So what I have here on the left, or on the orange graph, is the messages that are coming into SQS from Spark/S3. And in the beginning, there are no importers. So this green curve, which is the number of messages processed from SQS, the count is kind of low here. In reality, we actually have just one instance all the time. But for this demonstration, just assume that's kind of 0. And then this blue line is the total CPU of the cluster. And you can see some steps here as the autoscaler keeps adding more and more nodes. So what's happening essentially is the autoscaler is increasing the pool. And as it does so, the processing rate increases until there are no more messages to process, and it completes processing of all the SQS messages. And as I mentioned, so the metric that is used for autoscaling to scale out is average CPU. So our scaling policy is that we tell the autoscaler, never let the average CPU go higher than 40%. If it does, add more machines. And so what it does is it'll keep adding machines to keep that CPU at around 40%. You can see that it does a really great job of doing that. So it's always getting ahead of the load. There is one problem with this approach. CPU is actually not a great metric. When you get down to the last message in SQS, let's say you've scaled out to 20 nodes. 19 of the nodes are idle, and their CPU is basically around 2%. And then one node is like processing the last batch. And our scale-in policy is something like when the average CPU falls below 10%, hey, autoscaler, start killing nodes. And that's what happens. The autoscaler doesn't know which node is the one processing the last message. It just starts killing nodes. And sometimes it kills the importer that's processing the last message. And what happens is we get this really long tail of processing the last message. And it takes a really long time. So this is called premature scale-in. So the idea was CPU is not really a good measure. So we tried a different one, and it's called the queue-based approach. So when you're reading messages from SQS, messages are in two states. They're either visible or they're in flight. If they're visible, it means a GET request on that queue will give you a message. If it's invisible, it means no GET request will give you that message. It's invisible for a certain timeout period. So what we have here is this first blue curve right here is the count of visible messages on the queue. So as Spark is working and producing messages, the number of visible messages increase. And our scale-out policy is as long as that value is greater than 0, scale the cluster out, make it larger. And at this point, what happens is the cluster starts processing messages. And they go in flight. That's the orange curve. These are in-flight messages. And Spark stops creating new messages here. And now we're just basically consuming them. So this drops to 0. And when we hit 0, we stop scaling out. The cluster is now at its maximum size. And then we wait until all the in-flight messages go to 0, which means that they've all been processed. And then we magically just immediately scale in our entire cluster. And this worked very well for us. We no longer had this crazy long tail. We essentially scaled out while there was messages to be processed, and we scaled in when there were no in-flight messages left. So some people ask, like, how do we, what's the cloud-native approach to building these auto-scaling groups? So we've adopted three major tooling, languages or tools. So the first one is called Terraform. How many of you have used either Terraform, Ansible, or Packer? Excellent. So Terraform is the way to allocate resources like SQS, Kinesis, EC2. They basically, in a declarative model, they're actually all config as code, but they essentially give you an SQS resource. And that's essentially the tool to allocate these Amazon or GCP resources. Once you get an EC2 machine, you have to install probably some Ubuntu packages and some like Python packages to make it useful for you. For example, our data science, like our Spark clusters that we build the AMIs using Ansible and Packer, and essentially those we have to basically get a vanilla instance, and then we install like SciPy or scikit-learn or like other packages, maybe Java, so Ansible is the way that you would provision a single EC2 machine with all the packages, OS and Python that you need to run your application. And finally, Packer is this tool also by HashiCorp that will generate an AMI for you, an Amazon machine image from everything that you've built. So let's have an example. Let's look at an example. So step one, we run Packer, and Packer will create an EC2 instance with basically it's a blank canvas, just like a very some like blank basic Ubuntu 14.04 image on it, and really nothing that your application needs. And then we will run an Ansible playbook to provision whatever your app needs. Like if it's a Python app, it's going to need like a lot of pip install packages and maybe a couple OS packages. And then we will Packer will take a snapshot of that machine and register the AMI with Amazon. And then it will destroy the machine. It really doesn't need the machine beyond just baking this AMI. And finally, Terraform, along with this AMI, will, in like a blue-green fashion, will spin up a new autoscaling group and launch config with this AMI and replace your existing autoscaling group. So it does blue-green deployments. And this is essentially how we deploy all of our autoscaling groups today. So this sort of covers the timeliness and cost aspects of our bash pipeline. What about operability and correctness? So when we first started, our data science team was essentially writing cron jobs to run our like Spark jobs. And it's not ideal in many ways. So we needed a better way to author, configure, and manage workflows. And we also needed visual insight into the performance and correctness and state of our workflows. Like for example, was a given task failing a lot and constantly being retried? Is that why our SLAs were taking longer and longer to complete, right? And also we needed some really good integration with our existing alerting, so we could page an on-call engineer to have a look at one of our failing workflows. And the best solution we found, this is probably about 2 years ago, was Apache Airflow, which was just starting at that time. It wasn't even in Apache. And so this is what it looks like. So given a given workflow or a DAG, it's nothing but Python code. It's just very simple Python code. And when visualized, it looks like this, right? And the DAG that you're looking at essentially manages the batch workflow or the batch architecture shown on the lower right. And say you want to, you want some insight into the running of your pipeline. So you get a Gantt chart for each and every run. And what this shows you is that the longest step, and we sort of talked about it, the longest step is the Spark aggregation and scoring that happens. And then after the aggregation is done and this data is sort of being pumped into S3, the importers will complete it. So this takes about 10 minutes. This takes about 1 minute, right? So and then we also have sort of a wait for S3 thing here because S3 has a known like consistency, like eventual consistency issue. So to avoid it, we actually do kind of just a timed wait. And essentially this whole thing takes around 20 minutes or less to run. And what if you want to know that, hey, this is pretty fast for our hourly pipeline. We're completing it within the first 20 minutes of every hour. Of course, we're paying for the full hour. But is it always running efficiently? And then you can get sort of a task duration chart which will give you a historic view of the running of your pipeline. And each of these lines represents a different task. So again, this is the most expensive task. This is the aggregate Spark job. And what we find is the first month of, I think last year, it was just getting linearly slower. And there was a bug, and the data science team found it, fixed it, and then we got basically over the next 4 weeks, consistent run times of our Spark job. I mean, at this point, it's taking over half an hour to run it, and they brought it back down to around 10 minutes. Then they did another optimization, and they brought the time down even further. So one thing that happens, at least in data science, is that it's like a virtuous cycle, right? They're using new features, and sometimes those features are not performing like they would expect, and things get slower. And then they have to do some like cleanup to bring the times back into alignment. And essentially, this is a new feature. Then these are two optimizations, and then they added another feature, and again, time went up. So things like Airflow give you that ability to maintain this virtual cycle of new feature development, new data science like models development, as well as like performance optimization. Now, what happens when your pipeline takes longer than an hour? Or what if your pipeline generates some sort of errors? In that case, we have integration with Slack, and we use like ChatOps and SlackOps. Airflow basically like will dump into here. Like this says we're missing our hourly SLA, and this one says, guess what? We've lost data. And then we'll actually page our on-call with integration with VictorOps or whatever, a PagerDuty. And then they'll be notified that something's wrong with the pipeline. And Airflow meets all of those needs for us. So essentially, this is how our batch pipeline runs. And with Airflow, we get the correctness and operability that we need. How about our near real-time pipeline? So the way our near real-time pipeline runs, again, we have 3 customers. They are dumping data as they get it into Kinesis. Kinesis is Amazon's answer to Kafka. And we have an auto-scaling group of scorers that are getting this data within microseconds in most cases of when they were actually dumped onto when our customers got them. And we score the data and write the scored data out to another Kinesis stream where importers will read it and import it into our Postgres database. And then they will also send it to another Kinesis stream, which will be read by our alerters. And our alerters are responsible for doing a matching on customer policies to see if an alert condition has been met. And if they have been met, they may take an action like quarantining the email on the sensor across the internet. And this is our real-time pipeline for our control system. Similar to this, we also have some upgrades to this pipeline. This slide already was kind of busy, but you can imagine that we also have Elasticsearch in this mix. It reads another Kinesis stream downstream of the importers. And I'll talk a little bit about that now when we talk about the components. So again, S3 is our data lake. Okay? It stores, even though data is coming into Kinesis, we use Firehose to write that data to S3 because our model building will go against the data in S3. We still do full model builds every night. Instead of SNS SQS, we could have stuck with it for messaging, but because the whole world uses Kafka and we didn't want to be so innovative, we decided, OK, let's go with something that's a hosted Kafka. We went with Kinesis here. And again, it's serverless, something we don't manage. And it's worked fine for us. In retrospect, I think we might have been able to do SNS, SQS, and it might have actually been better. But one thing we looked at was the message size. And at that time, we were concerned the 64 KB size limit on SQS messages might have been too restrictive. And with Kinesis, you get, I think, 1 MB. So that was one of the reasons we went with Kinesis. For general processing, we've started moving everything to Lambda for the cost reason that I mentioned. But Lambda only supports like Python, Node, and Java. We still have a bunch of stuff in Ruby. And for that reason, we still run the autoscalers. And sometimes there's also a limit of memory The largest Lambda you can get is like 1.5 gigs of memory. And some things we do may require more than that because we'll map a huge model into memory and we might end up using more memory. So that's like the second use case for using an autoscaler over Lambda. Spark. So this is an interesting point. Our first cut implementation of our real-time system just took our Spark jobs for scoring and just changed the interface to use the micro-batch approach. And the job was written to run in 10 minutes. So it still ran in 10 minutes. But that didn't really help us for near real time. So we found the performance of the job was not better just because we had micro batches, because some of the operations in the spaghetti code that became our Spark code was doing some really inefficient things. And the amount of time to rewrite that job would have taken probably a year. Because, given, I'm not saying the data science folks were not like following best practices, but they were sort of, writing code with a free hand, and, they just knew they had to get stuff done in 10 to 20 minutes. And that code didn't translate well to running in the near real-time streaming model. So we took scoring and aggregation out. And we just use Spark now for model building. And we've actually moved the scoring directly into a Lambda. And I'll talk about the aggregation next. We still use Airflow for certain things like the nightly model build. We're still using the database to hold some data. But what we've done is, so because we went near real time, we could no longer do this aggregation every hour. Our users want real-time aggregation. And the other problem with doing hourly aggregation is what you're essentially doing is a pre-aggregate. Some data lands in a details table in Postgres, and then your Airflow job is saying, compute a pre-aggregate for that 1 hour, and data comes late. And when data comes late, your aggregates are completely wrong. So what we did was we just killed pre-aggregation altogether, and we put Elasticsearch downstream of our database, reading off a change capture stream, and we just do on-the-fly aggregation, 500 million data points, and it turns out our web app is 100x faster and is more accurate. So we actually, we follow this approach of like polyglot persistence, where we say your relational database doesn't have to do everything. If you have a relational database and a change capture stream, downstream you can put whatever you want. It could be a graph engine, it could be a search engine, it could be whatever. And we currently put Elasticsearch downstream to do both search and also aggregation on the fly. And that's been a huge win for us. So what sort of other innovations have we come up with when we started building this NRT pipeline? Oh, I should mention that the Elasticsearch that we're using is the hosted Amazon Elasticsearch. We, again, don't manage it, so it's completely serverless. I don't know why I said managed. We should actually say serverless for that. And we also did one other thing. Our Spark jobs for scoring needed to do some windowing functions. And what we actually do is we store data in Elasticache, again, the Amazon Elasticache. And instead of going to Postgres or writing some complex Spark code. Right. So how many of you use Avro? OK, not a huge amount. How many of you know what Avro is? OK, still not a huge number of people. And how many of you work in finance? OK, well, interestingly, the one who raised his hand works in finance. OK, so I've talked to a couple of people about this. And typically, the people in finance don't have this exact requirement that you find in Silicon Valley, which is that the market closes. They have a downtime. So I'll talk about that right now. So Apache Avro is a self-describing serialization format. So think about when you put data in a database and you access that data. There's a schema around that data, and there's some sort of code that's validating that all data in or out matches the schema. But what happens when you have a data pipeline, and two processes are communicating through a file on the file system, right? Or they're communicating through a pipe where data is streaming through. What guarantee do they have that the reader and writer are using the same schema? Like, do they agree on the types of the fields in that data? Do they agree on the cardinality of the fields? this is the problem that Avro solves, right? Avro applies a schema on top of data at rest or streaming, so that there's a contract and data doesn't get corrupt. So it supports primitive data types, int, long, boolean, float, string, that sort of stuff, complex nested data types, records, arrays, unions, maps, and it has language bindings to various languages. At least until recently, I would say it was the most common structure format like used for big data. But now I guess we're seeing more and more Parquet, right? But it was definitely for a long period of time the format of choice. And it supports schema evolution. So why is it useful? All right, so Agari is an IoT company, okay? We have sensors deployed in our customer sites. Those sensors are upgraded at different times. We have no control over when a customer will upgrade their sensor. So they're all running different versions of the code, and they're actually sending different versions of the format to us, right? So maybe version 1 is sending 3 fields. Version 2 has added 2 more fields to the data sent to us. And version 3 has added 2 fields and dropped 2 fields, right? And at any given time, that mix of data formats is coming over Kinesis to us. And to make matters slightly more complicated, the version that we're expecting on our side is a different version as well. So very early on, before we even had our first customer, we picked Avro as our serialization format to support this specific use case. We should never know the format of the data coming over the wire. It should be transparent. And the way this is done is the code in the server is sort of compiled against version v4. And the code running on all these consumers is compiled against different versions. We call one a writer schema version and one a reader schema version. The readers on the is on v4, and the writers are on v1, v2, v3. And when the reader has to read the code, it hands in both the reader and writer schema, and it gets a clean union of that data and never needs to worry about it. So as long as the writer schema is passed with every message over the pipe, and the cloud-based service has access to it, it can do the schema resolution, and we never have to worry about backward compatibility. And we do enforce backward compatibility in a Jenkins job. If you have questions, I can talk about that afterwards. So it became so useful as a tool to shield us from data format issues with our customers. We used it inside our pipeline for every step. So all our processes are decoupled from each other, not just by virtue of using queues like Kinesis, but also because the data format supports automatic schema evolution. And because we're a Silicon Valley company of 20 engineers, we need to have at least 4 different languages. So everything is written in a different language. Rails, Python, and Java are all involved in decoding and encoding stuff and setting stuff in the pipeline, and we have Node.js now. So, and luckily that also supports Avro. So there are language bindings for all of these languages. So as an example, this is a schema, an Avro schema. You have a record type. We're calling that Agari.user. It's a user record. And the user record has the name, as well as the user's favorite number and the user's favorite color. And the first field is a required field. The name is required. And the second 2 fields, favorite number and favorite color, you'll see it has this weird notation. Looks like an array of int and null or string and null. It just means it's an optional field. So as I mentioned, Avro is very common in the big data world. And is typically used to write large files at rest on like HDFS, where the block size is like 64 MB. And the schema is placed at the top of the file as JSON. And then there are just datum in binary written below it. And when you have a million or billion of these records, the overhead of the schema is tiny, like 0.00001%. It's like very, very common as an overhead for the schema. But what happens if you're streaming one record at a time over Kinesis, right, or Kafka? In that case, the schema is 99% of your data. You actually don't want to send the schema with every single message that you send. This is overhead. So one thing that we've, I think the last time I gave this talk, I promised I would open source this, and I haven't got around to it. So I'll promise you yet again that we're going to open source this, is a schema registry. It comes with like Confluent. There is like an implementation. We've implemented something on a Lambda that is like very effective, very lightweight. Essentially, we have a Lambda, and it has two functions. So sometimes people talk about it's a function as a service. We actually don't follow that model. We actually dispatch to multiple functions in a Lambda. And so one of the functions is register schema. So in this case, a producer, before it sends a message down the pipe, will register a schema, and it'll get back a unique ID, in fact, a UUID. And it will then send that UUID plus that datum across the wire, and the consumer will get the ID and the datum. So the problem is it's got this data. It doesn't have the writer schema yet. It has an ID to get a writer schema. It will then do a lookup by get schema by ID, get the writer schema, and cache it. And then it will use that along with its, what it compiled against the reader schema to decode it on the fly. And that's essentially how we use it. So in every place we use Kinesis, we have this Lambda schema registry, and we cut down on all the time taken to process this data. All the time spent in transmission and processing. So I think at this point, I'm actually ready for questions. Of course, none of what we've done is a single man effort. Multiple people in my team have been helping. And any questions you have?
I wanted to clarify, when you're talking about Lambda, you were talking about AWS Lambda, not necessarily a Java Lambda.
Yes, the question is, was I talking about AWS Lambda or like a Java Lambda or functional Lambda? You're right, AWS Lambda. Thank you. Go ahead.
You mentioned that in retrospect, SQS and SNS might have been a better approach than Kinesis. Do you mind elaborating on that?
Sure. OK, so the way Kinesis works is that it's very much like Kafka. You get partitions, and each partition is provisioned with a very strict I/O limit. And let's say, so for a given partition, you can do 1,000 puts a second and 5 reads a second. OK. So what happens when you exceed that? Well, you get throttled by Amazon, right? So you have to, so when that happens, you have to scale out your shards, okay? The problem with the scale out of these shards is that the way Amazon, they do what's called a split of shards. The way they split the shard is they put an end of shard marker in the old shard and create 2 new ones, splitting the key space. They don't actually cut the amount of data on the 2 in half. They don't like divide the shard, move the data on the half. So what they do is they just end the current shard, and they create 2 empty shards now. That's what a shard split is in Amazon. Are you following that?
Yeah.
Yep.
They're not just finished processing the data.
Right. So now what happens typically is when you find that you're in trouble with a shard, it's typically on the reading side. You're fallen behind in processing on the reading side. And there's a huge, you're like behind by, let's say, 8 hours or a couple hours. You're just behind by a couple hours. Splitting the shard doesn't help you. You're still behind. You don't magically get 2x the read capacity that you needed. So that's one problem. They say that shard splits are very cheap and fast, and this is why they're cheap and fast. They're not moving the data around. The second problem is no one should have to worry about this, right? With SNS and SQS, you get magical automatic horizontal scaling. It shouldn't be provisioned I/O. And so had we stuck with it, we could just process everything in parallel and never have to worry about, this is our expected capacity, and this is how much we provisioned. And so what we currently have is an Airflow job that does like preemptive scaling. When we're close to hitting a boundary, we start adding shards. And we need a job to maintain that. In the SNS SQS model, it just automatically scales under the hood. Amazon itself keeps adding instances when internally it's hitting 80% capacity on any one of the SQS partitions. That's what we would like. Did that answer your question? OK. In the back? OK, so his question is, in our implementation of the schema registry, are we always caching the writer schema on the consumer side? Or is it a lookup per object? So the answer is, yeah, we're always caching. And interestingly enough, half of our functions have moved to Lambdas. And those lambdas are calling this lambda. And this is how we found out our lambdas are very long-lived. Because they're all lambdas reading from Kinesis, they live for 3 days. So the hits to the schema registry lambda from one of our normal processing chain lambdas are very low. They cache for like 3 days. Does that answer your question? OK. Go ahead. OK, so that's a really good question. His question is, what is the scale that we are seeing? The scale that we are seeing is tens of millions an hour, sometimes more. Depends on the hour of the day. And some things that we do, like some parts of our code we have to reprocess, and we can push 400 million through in about a day, like on a reprocessing use case. If we have to make a change to our scoring algorithm or something, we sometimes reprocess. I mentioned we have Elasticsearch. If I add a new field and we maintain 60 days of data, 60 days of data for us is 500 million records. So if we add a new field, for that one Kinesis hop, we have to basically push 500 million records in, and it takes about like a day. Any other questions? Perfect, great question. So his question is, what's the trade-off of EMR versus self-hosted? So it took us like an hour so the problem with EMR is we cannot specify our own AMI, right? So we would get the EMR AMI, and then we'd start installing like tons of Python packages. It would take 40 minutes. And then we're ready to use it, right? So so that was the major problem, like that spin-up time. So that's why we moved away from EMR.
OK, maybe we should stop a little over time. Thanks again.
Thank you.